My name is Ayden Pugh, and for my senior project, I did a climate trend analysis of Washington State. I've lived in Washington my whole life, and I'm very fond of it. And I've wanted to study meteorology since I was 12 and had to do a science project on tornadoes and discovered the beautiful, complex chaos that is our atmosphere and just fell in love. And so this was a very natural combination for me of two things that I love. Washington has a really interesting climate because it's divided by the Cascade Mountains, as you can see on this map. And this kind of divides the state into two very distinct climate zones. So the western side of the state is what most people think of when they think Washington. It's very green and moist. The temperature is pretty moderate. It doesn't get too hot or too cold. But the eastern side of the state is very different because of the Cascade Mountains. So as air moves east across the state, it hits the mountains and is forced upward. And as it rises, it expands and cools, and eventually the air becomes saturated and the water vapor condenses, and then it precipitates. So all the moisture in the air is dumped on the western side of the state and in the mountains. So by the time it gets to the eastern side of the state, which is where I'm from, it's really much drier. So eastern Washington is in some places even desert-like conditions, like this. These are the scablands in central Washington, and lots of it's uninhabited. And other than a lot drier, there's much more extreme temperatures, so it gets really hot in the summer and really cold in the winter. So I was interested to see how Washington was changing as a whole, but also how these two different climate zones were changing. So what I did is I took daily temperature, maximum, minimum, and precipitation data from 37 stations across Washington State in these locations. And I used this data to calculate climate indices. And climate indices are annual values that quantify observable climate extremes. So when it gets really hot or really cold, or when it rains for a long period of time, or it doesn't rain for a very long period of time. And I took these indices and performed a statistical trend analysis on them to see how the climate was changing over the last 100 years, roughly. And my main result is that it's getting colder less. The indices that were measuring cold days in the winter had much more significant trends than the ones in the summer did, which is consistent with many other studies done. Specifically, the number of frost days is decreasing across the state. This map shows the location of the stations with statistically significant trends, and the circles correspond to the magnitude of the trend in days per decade. And as you can see, in some places, they're losing over 4 days frost days per decade. And a frost day is defined as a day where the temperature minimum is less than 0 degrees Celsius, which is the freezing point for water. I also found that the percentage of cold nights is decreasing all across the state as well. As you can see in this map and the previous map, they're kind of clustered in the western side of the state and in the Cascades, which is important because of the snowpack of the Cascade Mountains. And snow plays two very important roles, the first of which is that it's a temperature moderator. Solar radiation comes in and is reflected by snow, so it's not able to reach the ground and warm the ground. But if the snow melts, more solar radiation is able to reach the ground and warm it, which causes more snow to melt, which causes further warming. So a loss in snowpack is able to amplify warming trends that are already present. And this is also important because eastern Washington, being so dry, its river systems rely in part on the mountain runoff to supply it with water. A large portion of eastern Washington is irrigated through the Columbia River system, and that's where most of our agriculture takes place, so apples, potatoes, lentils, wine is all used through irrigated crops, and a decrease in mountain runoff could lead to a decrease in the river system water, which not only provides water for the agriculture, but also drinking water. So it's interesting to see that while the change is mostly in the western side of the state, it's the eastern side of the state that could potentially have the largest impact on. And so that's the main findings of my study. And what's next for me is I'm going home for a year to take a gap year, and then hopefully to graduate school, where I'm thinking I'm going to focus in cloud and precipitation microphysics. Thank you.